All right, so for the section 5 of this chapter 4, we are going to introduce a new technique for integration. And if you don't mind, let me say a couple quick things. So if you have more math in front of you, say the second semester of calculus, maybe third semester more of calculus, the second semester is where you'll learn a lot of various integration techniques. And what it'll come down to is there's certain integration techniques that you won't see very often after you've been introduced to it in Calculus 2, right? There's certain integration techniques that are very specific, and you don't see them show up as often in your following math classes. Very, very, very specific techniques for a very specific integral. Then there are other techniques, like the one that we're going to learn now, actually, where you will continuously use this technique. So this is, if you have a lot of math in front of you, this is a technique that you really, truly want to master. Now, all I want to do is, if you don't mind, put your pen down for just a second and just relax. I want to show you something. So remember this integration technique where if you were integrating x to the power of n, you would have x to the power of n plus 1 over n plus 1. Can I anticipate something now? I know that there's the caveat there was a caveat that obviously n cannot equal negative 1. But here's something. Now, most students intuitively understand why you add 1 here, right? I mean, when you take a derivative, you subtract 1, and if an integration is just the inverse operation of differentiation, then most students can understand, okay, well, I understand why you add 1 here, because you were just done subtracting 1. So that would undo that. But a lot of students don't quite understand this part. Why do you have to divide by n plus 1? So let me see if I can do a why for just a real quick explanation. So let's start with just the steps of a derivative. So here's some basic y equals ax to the power of n. And how about you and I go through the 2 steps to take that derivative, okay? So the first step, remember, the first step you do is you multiply by the exponent, right? So this would be n times ax to the power of n. So that kind of the first step was to multiply. And then the second step was to subtract 1 from the exponent. So that would be n times ax to the power of n minus 1. Okay, so step 1, multiply by n. Step 2, subtract 1 from the exponent. No problem. Now, if you want to undo, right, I put in quotation marks, undo that derivative, then that would require that you undo each of these steps. So let's start with how would you undo step number 2? Well, what is the inverse operation of subtracting 1? Well, it would be adding 1, right? So for step 2, if you wanted to undo that, here you had n multiplied by ax to the power of n minus 1. Now, that's what you had. If you want to undo that, then you would have to plus 1. Right? Now, you see how that the plus 1 and the minus 1 cancel out? So that's how you would cancel out that step 2. And okay, let's go ahead and write what you would be left with. You would be left with n times ax. And of course, negative 1 plus 1 cancels, so that's to the power of n. Okay, so you just undid step 2. Now, how would you undo step 1? Well, what did you do in step 1? Well, you multiplied by n. So what would the inverse operation of multiplying by n be? Well, it would be dividing by n, right? So here's what you have right now, n times ax to the power of n. If you want to undo that first step in your derivative, you would have to undo times n. How do you undo times n? Well, you can undo that by dividing by n. And what you see here is when you do that, you're left with your original function, which was just ax to the power of n. So I hope that that helps helps you understand that process of that integration technique that you've been using so far in chapter 4. And now we introduce a new technique. And I've already at least tried to sell you on the idea that this is one that you do need to get good at. You really, truly need to get good at. If you don't believe me, ask someone who's taken Calc 2 and Calc 3 and ask them, what integration technique did you use the most? See if they don't say U-substitution, okay, or integration by substitution. And you ask anybody who teaches your Calc 1, Calc 2, Calc 3, almost inevitably, or student, you can ask a student too, almost inevitably everyone will say that Calculus 2 is harder than Calculus 3, and it is. At least I can say that I lose more students in Calculus 2 than I lose in Calculus 3. Ready? So I'm going to teach one technique. If you watch various people do this on YouTube, you might see this written differently. But I'm going to show you, in my opinion, the best way of doing the U-substitution. Now, so what do we mean? Anti-differentiation, but using the integration by substitution. So look at what's inside this integral. Do you remember the chain rule? Wasn't that f prime of u times u prime? You seen that before? F prime of u times u prime, right? That was how you would take a derivative of a composite. You want to undo that. So that would be the result. You would have your composite. Again, there's your constant of integration. Don't leave that off. You have to have plus c, otherwise you're lying. You're saying, if you leave it off, you're saying c is 0, and you don't know that. So let me now just jump to the work. So our first problem is we'd like to integrate 5 cosine of 5x. So listen, some of you are very savvy at doing math in your head, and you might be able to think of the derivative or the function out there you took the derivative of to get this 5 cosine of 5x. You might be able to do this in your head. I'm asking you not to, because I'm asking you to, when this gets tougher, you're going to need this technique. Ready? So here's what we're going to do for U substitution. We're going to let u equal the, let me just jump in for this problem. We're going to let u equal 5x. Now, y, how about we hold off on the y for just a second? Now, as soon as you tell me that u is equal to 5x, you have defined 5x to be defined as u. So wherever I see a 5x, I can insert a u. So I'm going to take my time on this first problem because I want you to see it. So right now, I'm going to insert u for this 5x. Let's rewrite our integral. So the only thing that has changed as of right now is instead of having a 5x, I now have u. Okay. Now, I can't, let me erase that. I can't integrate this the way it sits. Why? Because I can't integrate u's with respect to x's. That makes no sense. So if I have variables u, then I need to have du here. Do you understand what I'm saying? So this has to be a du for me to integrate a u. All right, well, so let's get back up to here to our substitution. So we said u was equal to 5x. Now, the derivative of u with respect to x is what? Well, it's 5. That's beautiful. Except I'm not really interested in the derivative of u with respect to x. Really what I am interested in is this du. That's what I want. So now you're seeing this Leibniz notation put to use here. We're gonna take this dx and we're gonna bring it to the right side of this equation so that we have solved for du. Are you ready? Let's do that. So now du would be equal to 5 dx. Okay, now let's come back over to our problem. So I want this dx right here to become a du. But let's look at what's required to do that. So in order for me to put a du into my integral there, I would have to have a dx. Well, that's okay. I have a dx. And I also would have to have a 5. But that's okay. I have a 5 as well. So what I want you to understand is this 5 right here and this dx right here are going to disappear because 5 dx is equal to du. Do you understand what I just said? Because I'm going to say it again. This 5 is going to disappear and this dx is going to disappear. And what's going to appear is this du. Why? Because du is equal to 5 dx. Ready? Let's do that. So now I have the integral of cosine of u. And then where did the 5 go? Where did the dx go? Well, 5 dx is equal to du. Do you understand how U-substitution was able to take what was at first sight a somewhat hard integral, and now this is an integral you've seen in your previous lectures. This is definitional. So let's integrate. Let's go ahead and integrate. So the integral of cosine is sine. So this is sine of u plus c. This is definitional. You can look up what the cosine of u is. It's just sine of u. The cosine of x is sine of x. Don't forget your plus c because you integrated. Now, if you left it here, if you left it alone, then only you understand what you've done, okay? Because your client asked you to integrate 5 cosine of 5x. Your client has no idea what the heck a u is. I mean, they understand what an x is, but they don't understand this. So the very last step is to take the u and to write it in terms of x. So we plug that 5x back in, and the result is sine of 5x plus c. That is the result. Now, here's the good news. Let's assume that you're taking your final exam and you start to second guess yourself and you don't know if this is correct. Well, what could you do? Well, why don't you take a derivative? And if you take a derivative of your result, you should get back this 5 cosine of 5x. And in fact, you can do that on your own time. You would get it. The derivative of c is 0. and the derivative of sine of 5x is 5 cosine of 5x. Okay, now I don't have time to reteach you basic differentiation, but I hope that you can understand the substitution process. Let's go to the next problem. Ready? Okay, so the practicing of choosing a good U is something that you have seen before when we were doing the derivatives of composites. I spent a little bit of time, quite a lot of time, just asking you to practice what should I pick for U. So hopefully this part here is somewhat easy. So we're going to let U equal what? Well, we're going to let U equal x squared plus 1. And now to kind of expedite the process, I'm going to go ahead and find du right now because I know that I'm going to have to do that. And again, to expedite the process, instead of having to bring the dx to the right side, like I did on that last problem, are you listening to me? Instead of having to dx here and then me bringing the dx to the right side, I'm just going to write this at du is going to be equal to something dx. Ready? So what is the derivative of u with respect to x? Well, the derivative of x squared is 2x. Right? And the derivative, and then we're going to bring that dx over. So the derivative of 1, of course, is 0. So the derivative of x squared is 2x. The derivative of a constant is 0. And are you with me on how that, I'm going to do it one more time for you. Are you with me on how that dx can be brought to the right side? I'm not going to do that anymore. Du is equal to 2x dx. All right, I'm going to box in these two important pieces. And now, this is an important problem. So let's go ahead and start. So I'll start with just the u. So this x squared plus 1, henceforward, you have defined it as u. So I'm going to replace x squared plus 1 with a u. Let's see what that looks like now. So now we would have the integral of x, and we had an x squared plus 1, but now we have a u squared dx. Okay. Now, what we want is we want this dx to become a du. So hold on for a second. I need you. Are you with me? Look right here. Look. Follow me here. I need to have a 2. I need to have an x, and I need to have a dx. I need to have all three of those in order to substitute a du. Let's start with what we have, and then let's identify what we do not have. Do you have a dx? Yes, we do. Do you have an x? Yes, you do. What are you missing? You're missing the 2. So how can we get around that? Well, look, if I had this, let's let that x be your age. Okay? Now, if I take your age and double it, while also cutting it in half at the same time, don't you agree with me that I have not altered your age? We're going to do the same thing. We have the x, we have the dx. We're missing the 2. So watch, I can put a 2 here. Now, I can't take your age and double it unless I also cut it in half, right? Otherwise, I just doubled your age. So in other words, I can put a 2 here as long as I put a 1/2 out here. Because what's half of 2? It's 1. You see the manipulation? So let's actually write it. So I'm going to go ahead and write everything. I'm going to give myself enough space. And here we go. So I'm going to put a 2 right here because I need it. But I need to compensate for doubling by halving. Are you with me on that step? That little step is called the constant multiple rule. Okay. So what's going to happen right now? Well, I have a 2, I have an x, and I have a dx. Now you've already said that if you have a 2 and an x and a dx, you can substitute a du in for those three things. So this 2 and this x and this dx are going to disappear, and this du is going to appear. Ready? Let's go ahead and rewrite. So the half is going to stay there. And oh, the 2 is gone. The x is gone. The dx is gone. And what's left? du. All right. Now, again, what started as a complicated integral, now this is just a power rule, right? This is just integration you've been doing all along. So let's finish it. So this is going to be 1/2. Now, if you integrate u squared with respect to u, that's going to be u to the power of 3 over 3 n plus c. Beautiful. So I'll go ahead and distribute that half. So that's u cubed. 2 times 3 is 6 plus c. Ready? I hope you're anticipating that last step. So that last step is take that x squared plus 1 and put it back in here for this u. Then you're done. X squared. Be careful. Make sure you use your grouping symbols. I almost forgot myself. X squared plus 1 cubed over 6 plus c. All right. You are now integrating by substitution. So we're going to practice one more of those constant multiple rules, and then we're going to run into a problem, because you know what your math teachers like to do. They like to build up your confidence, right? And then they like to just rip it away with a hard problem. So let's go ahead and do one more of those guys. All right, let's start to pick up the pace a little bit. So let's see if you and I, the first thing I'm going to do, I don't want these radicals. Look, in case no one took the time to tell you, that symbol is just, that square root symbol is a way of writing something to the power of 1/2. Literally, this symbol right here this symbol means something to the power of 1/2. That's what this symbol means. The square root of means to the power of 1/2. Okay. Now, what I've done right now is talk without writing the 1/2 here. All right. So what I have at this stage is 2x minus 1 to the power of 1/2. And now we start our u substitution. All right, so let's let u equal the 2x minus 1. Ready? Now you know du. Let's take the derivative of u with respect to x, and we're going to put the dx on the right side. So the derivative of 2x is 2. The derivative of minus 1 is just a 0. So we end up with 2 dx. All right. So as of right now, let's go ahead and rewrite our integral. Okay, as you get good at this, you don't have to do this step right here where you put a u, then you put a you don't have to do this. You can jump right to the du part if you know how to do it. Okay, you'll get better. You'll get faster at this. I'm taking my time to show you. All right, so the u substitution is done. I plugged in the u. Now let's look at du. So in order to substitute a du, I need a 2 and I need a dx. Now I have the dx. What I do not have is the 2. All right, so hopefully you can anticipate what's going to happen. I can put a 2 here, because that's what I'm missing, as long as I compensate by having that 2 out here. Half of 2 is 1. All right, ready? So now we have the integral of u to the power of 1/2. And as of right now, this 2 and this dx, both of these are going to become du. They get both of those, that 2 and that dx disappear, and that du goes right here. All right, let me not forget my 1/2. Okay, well, we got this. This is not bad. This is just going to be 1/2. And now let's go ahead and integrate. So u to the power of 1/2, it's going to be u to the 1/2 plus 1 over, over 1/2 plus 1. And I'm going to go ahead and write plus c. All right, let's clean this up. Right, this is sloppy. Look, you got 50 cents, you got $1, you got $1.50. $1.50 is 3/2. So, and now I'm going to show you. I'm going to show you a trick that you should. Well, it's up to you, but I think you'll, if you heed my advice, you'll thank me later. So, 1/2 plus 1 is 3/2. When again, 1/2 plus 1 is 3/2. Now, I don't like to divide. How do I put this? Let's go back to, I don't like to think about division. I like to think about multiplication. So I don't think about x divided by 2. The way I would think about x divided by 2 is 1/2 times x. That's the way I would think about it. And likewise, I would not think about dividing by 3/2. I would think about multiplying by 2/3. So, optional, but we get 1/2. Now, to divide by 3/2, is to multiply by 2/3. Now, the only thing left to do is to take this u and get it back in terms of the x, right? And then maybe clean it up a little bit. So let's go ahead and I'll change my color here. So just follow me. I'll put a pin here, and you follow me up here. Okay. So 1/2 times 2/3, and let's get that back to x. So 2x minus 1 to the power of 3/2 plus c. Okay. Let's go ahead and distribute the 1/2. So 1/2 times 1/2 times 2/3 is 2/6, which will reduce to 2/6 will reduce to 1/3. So that's 1/3, 2x minus 1 to the power of 3/2 plus c. All right. So next problem, last problem of this section. So remember this constant multiple rule we were using, where you would multiply by 2 and divide by 2 at the same time? Now that does not work for variables. How do I say that? So you can't multiply by x and divide by x at the same time. That doesn't make sense. Okay, so let's go ahead and do a problem, the last problem. So let's start, because normally you won't recognize there's a problem until you start. right? That's why it's so important when I give you those homework problems, and I don't grade them, right? But what you have to understand is that the only way you get better at this is to start making some mistakes, and you want your mistakes to come when there's no penalty, right? A risk-free environment. Well, your homework is a risk-free environment. You can get in there and mess up, figure out what you're doing wrong, and then you won't make those mistakes when it comes to test time, right? You wait until you take your test, and then now you're going to have all those errors when it counts. So, as I said, you won't notice that there's going to be, normally you won't notice that there's going to be some trouble until you jump in and start trying it. Ready? So, first thing I'm going to do is rewrite this without that radical, so to the power of a half. Okay, so no calculus so far, and now let's start our U-substitution. So, just like before, you let U equal the 2x minus 1. Everything seems to be nice and neat. And then you say du is going to be equal to, well, derivative of 2x minus 1 is just 2. And then you went ahead and put a dx there. All right. So let's go ahead and start this process. So everything seems innocent. You go ahead and plug in, well, 2x minus 1, you're now calling that u. Everything looks nice and neat. And then you come over here and you're saying, oh, okay, hold on for a second. I want my du. And then you're savvy and you say, oh, okay, I got a dx here, but I don't have that 2. And then you're thinking to yourself, oh wait, that's okay. I can multiply by 2 and divide by 2. But then you're like, wait a minute. I have an x. I don't have an x here. Well, you do not get to divide by 1 over x, right? That doesn't work. You can do it with variables. So ready? Here's what we're going to do. Let's go ahead and start with the du. In other words, let's leave this x for the very last. We'll deal with that in just a second. Ready? Here we go. So we have x. We still have our u to the power of a half. All right, and here you go. You're savvy, and you say, okay, I got you. I'm going to put a 2 here, and I'm not going to get tripped up. I'm going to also divide by 2 here, so I can compensate. Okay, and now what's going to happen is that 2 and that dx are about to become du. Ready? So let's do that. So I got a half out front here. And I'm going to be integrating now. That x, I haven't done anything with that x. I'll have to deal with that in just a second. All right, so there's my u to the power of 1/2. Are you with me that this 2 and this dx are about to disappear, and a du is about to appear? All right, now let's stop. So at this stage, you're like, wait a minute, I can't integrate this, right? I can't integrate x's with respect to, I don't know why it switches to eraser when I don't want it to switch to eraser. If you know how to fix that, will you email me and tell me how I can turn that off? If you use one of these Apple Pencil styluses. All right, so here, I need to get rid of this x. More importantly, I need to get this x to be in terms of u, right? Because if I have a du here, if I'm going to integrate with respect to u, then the only thing that can be in here are u's, variable u's. All right. Well, how do we do that? Let's answer the question. Well, let's follow me down here. Remember, if you said you said u is equal to 2x minus 1, right? Understand, you said that. You defined that. That is true because you defined it to be true. But a consequence, if u is equal to 2x minus 1, then x is equal to what? Well, x would be equal to, well, you'd have to add 1 to both sides. So you would have, let's say that would be u plus 1 over 2. Right? Did I do everything right? So if you want to solve for x, you would add 1 to both sides, then you would divide both sides by 2. So wait a minute. If you see an x, you can sub a u plus 1 over 2 in there. Are you seeing it? All right, let's do it. Now again, I don't like having fractions. I like to think about multiplication. So to divide by 2 is to multiply by a half. Ready? So now I'm going to box this in, and I'm going to draw you an arrow because that is going in here. Let's rewrite. So I got 1/2 the integral. Oh, I used to have an x, but now I can have a 1/2 of u plus 1. And that's going to be times, well, I still have u to the power of 1/2, and I still have du. All right. So how do we finish this? So here's what's about to happen. First, I'm going to take this 1/2, and I'm going to bring it out front. So it's going to be a 1/2 times a 1/2. This guy right here is going to be brought out here. You with me? So I'll do that since the last problem. I'll go ahead and do that right now. So that would be 1/4. Wait a minute, where'd the 1/4 come? Because I'm taking the 1/2 and bringing it out here. A 1/2 times a 1/2 is a 1/4. Okay, so 1/4, and I still have my u plus 1 times u to the power of 1/2 du. Now what's going to happen right now is I'm going to multiply u to the power of a 1/2 times 1, and I'm going to multiply u to the power of a 1/2 times u. So let's do that right now. So that's 1/4 integral. Well, what is u? Let me, if you don't mind, let me give myself some space. So let's do this distributing. So u to the 1/2 multiplied by u to the power of 1 is obviously equal to u to the power of a 1/2 plus 1, right? That's just u to the 3/2. All right, so that leaves me with u to the 3/2 here. Plus, well, u to the 1/2 times 1 is just u to the 1/2. du. All right. So what's left is to integrate and then put back x, the 2x minus 1 back in there for u. So let me put a star here. Follow me up here. Ready? Let's do it. So this is 1/4. Time to integrate. Well, u to the 3/2 plus 1. Well, you have $1.50. That's 3/2. You add 1, you now have $2.50. So $2.50 is 5/2. So that's u to the 5/2 over 5/2. Plus, well, if you got a 1/2 and you add $1, you got 3/2, you got $1.50. So that's u to the 3/2 over 3/2 plus c. Okay, so what I'm going to do right now, we're done basically. I'm gonna take the 2x minus 1, put it back here for u, put it back here for u, and I also don't like this. I don't like this. I don't want to divide by a fraction. I want to multiply. So when everything is said and done, we have 1/4 times, well, to divide by 5/2 is to multiply by 2/5. And let's go ahead and put our 2x minus 1 back in here. To the power of 5/2. Plus, all right, well, to divide by 3/2 is to multiply by 2/3. And again, let's put our 2x minus 1 back in here. To the power of 3/2 plus c. All right, you're done. Now you could distribute the 1/4 if you wanted to. You could turn these fractional exponents. You could turn that back into the the square root of x to the 5th. You could turn them back into radicals. But does that make sense? Does that make sense where we left that problem? Okay, so we are done. On your own time, you can distribute the 1/4 if you want to. That's just 2 over 20. It's a 1/10, and you could distribute the 1/4 over here as well. Do you understand the challenge of integration? Right. I once heard. I've never heard it explained any better. That differentiation is fairly straightforward. It's here's the question, what's the answer? But integration is different. It's here's the answer, what's the question? And you will have to just slow down and take good notes and take your time and think of it as a puzzle, maybe, if you like puzzles. But we're going to go ahead and conclude. That is 4.5 on U-substitution, which is one of the most important integration techniques in all of calculus. And I suggest you get better at it by jumping into your homework. I will see you in the next video.